Hello, Michael. Can you hear me? Oh, I think you're muted.
Of course, this is Zoom
Uh,
tradition.
yeah. No, this is the first time we've changed to Zoom, so that's why it took a little bit to launch the meeting. But hopefully everything will be smooth
Wonderful.
from now on.
Wonderful. How are you?
Good, thank you. Thank you.
Um, Good. So, um, yeah, shall I share my screen? Shall we wait for a few minutes?
Yeah. Try to share your screen just to check that everything is working fine, and then yeah, shortly after that we can start, I think.
Okay, let's have a look. Can you see anything of note?
Yeah, we can see that. Okay,
Good, good.
nice. Yeah,
Um,
cool. Let me see. Uh, okay, I believe it's recording already. Okay, nice. Just checking that everything is fine because it's the first time we're using Zoom. Yeah. Cool. Okay, so today we have Michael Moutoussis. Is that how you pronounce? So he's going to be talking about Valence-partitioned inference and temporal difference belief updating for computational psychiatry. So yeah, whenever you want.
Thanks very much. In fact, you can sort of pronounce my title better than myself. I won't talk that much about computational psychiatry. I'm just going to touch on its psychiatric importance. So I hope that doesn't disappoint. But here we are. As an overview, I'm going to talk a bit about the social evaluation learning task, which some of you may know, and tell you a little bit about our journey from traditional associative models to active inference based models, which in this case I'm going to call classify, refine. And then I'm going to tell you a bit about valence-partitioned associative models and their application to this task. And then in the final part of the talk, I will say a bit about temporal difference modeling, and how I think this has got to do with updating values, beliefs, representations to actively attended states. And I'm going to sketch a Bayesian version of TD, or rather a TD propagation of Bayesian updates. So the problem in general is, how do we think, how do we infer about the positive and the negative in the social world? Um, this obviously has been discussed for centuries in different ways, but now we're doing it computationally. And this is the social evaluation learning task, or the core of it, that we have used as a workhorse for a while. And the idea in this particular version is that the participant is presented with a rater, who in this case is Sue, in this example, and they're asked, what do they think the probability is that Sue is going to find another character, here Fred, who appears below, to be characterized by a positive or a negative attribute. And so on each trial, they have to rate how likely they think it is. They're not actually asked to predict what is going to happen. And then they see Sue's rating, and they will update their beliefs for the next trial. So this is what happens again and again. And they have 8 different raters, like Sue here. And the ratee, which here is Fred, can be either themselves or another party or another avatar. So the basic condition here is self versus other ratings. And this is visible to the participant. And the hidden condition is that the rate can be either positive, neutral, or negative overall, but they behave probabilistically. And this is the overall framework of the task. Each block has got 20 trials that the situation that I've just described repeats. There is a framing which sets the sort of slightly believable or naturalistic setting to this. There is a beginning where people choose their avatar, so they identify with what's happening on the screen, and a global rating at the end. And this is the basic structure of the modeling, particularly for our Bayesian models. So we model the participant as having a model of the rater. And this is a hidden Markov model. So they update their beliefs about the rater based on whether the rater has just given a positive or a negative word as an outcome. And in most of our models, and that actually refers both to reinforcement learning, sort of traditional reinforcement learning ones, and basic Bayesian ones, there is a continuous scale that the rate can be positive to negative. And note that the participant has got no information about where to start from or what the distribution of raters is or anything. But based on their beliefs or the value of the rater, they make a reporting of the expectation that they have that the next time there's going to be a positive rating. And this is an example of the update or learning curves by the best Rescola-Wagner-like models that we made. And I have chosen two conditions here of the total of 6, where the model does not actually do that well. So you can see that particularly when the other is being judged, so it's not the self, it's someone else being judged, and the rater is a positive one, so it's an other-like condition, the model is pretty slow at approaching the levels that real participants that here are in gray and black actually tell us. So this is the basic Rescola-Wagner one, and this is our Bayesian model, which is based on a continuous positive to negative belief scale. And as you can see, it does better. So it doesn't lag underneath the black curve as much, but it still has got some difficulty. And it has got a much less sort of pronounced knee that the curves actually show. So this motivated us formulating these models, which were actually based on active inference, on the active inference framework, that the participants actually have got two discrete underlying states that they hang their clothes on, so to speak, a positive and a negative rater, and that this quick upstroke that we can see there is because they can very quickly infer with a little bit of evidence whether it's a positive or a negative rater, and then they actually update what it means to be a positive or a negative rater a lot more slowly. This has not come, the pictures have not come out very well, but here I'm illustrating the negative person with the Queen of the Night, and the positive person with the daughter of the Queen of the Night, who's a caring character in the opera The Magic Flute, just for fun. But the basic idea is that we've got in the green box there we've got the inference, is that the rates are negative or positive, and then learning what do these things mean. So the learning bit takes place by seeing what the outcome is and crediting the states that may have actually underlined this this observation in proportion to the belief that we have that these states were present. Okay, and this is characteristic of the active inference framework, but other sort of credit assignment schemes use this as well. And what we find is that this classify and then gradually refine model does much better than the other two. They're both the reinforcement learning classical Scholar-Wagner and the fine-grained Bayesian one. And you can see that by the fact that most of these dots, which are participants, are one side of the line, and here they are on the side where the BIC for the classify refine model is less than the beta belief, the fine-grained belief one. So my first question that I would be interested to discuss later is how fundamental this may be. Because you remember, we didn't actually tell people that the rates are going to be positive or negative or fine-grained or coarse-grained or anything. So is it the case that the social brain does use a few valenced categories, and then it has structure to those categories and refinement on top, but it uses a sort of rough categorization? And if so, is this because that might reflect real emergent relationships in the social world? For example, competitor versus teammate. So do we think that there is a deeper normative rationale for this kind of thing? So I now come to valence-partitioned associative models. So valence-partitioned associative models are a new thing in associative models, but of course the belief-based, the classify-refine model I described is by nature valence-partitioned. It starts by the idea that the underlying states are a positive and a negative one, but we have a key difference. And the key difference is that in the belief-based, active inference-based model that we have, this distinction is between the causative agents. The agent is either a detrimental agent or a beneficent agent, a beneficial agent. Whereas in the valence-partitioned associative models, it is actually the outcomes that are being kept account of. The positive outcomes and the negative outcomes are kept partitioned and separate accounts of them are made. So here is the basic equations for the valence-partitioned associative model. So what happens is we have two channels, a positive learning one about positive outcomes and a negative learning ones about negative outcomes. And each of those has a receptive field. So if something happens outside that receptive field, so here I have written an equation for the positive channel when there is a positive outcome. And that's a typical Scholar-Wagner style equation. But you will see that if the outcome is outside, if it's 0 or negative, if it's outside that receptive field, nothing happens. Okay, in the first instance, the value of that channel remains the same. So, and the negative channel is computed symmetrically. But of course, its activities, well, it's not necessarily of course, the activities that are being computed there are positive. So in each channel, a large amount of activity means a highly charged outcome. It doesn't mean a more positive outcome. And then what we do is we take these positive and negative values and we put them into essentially a softmax function. Here I've written it as an in-blogit function, but it's basically the same kind of thing. It's a logistic regression to model the rating that the participant gives us. Okay, so here you'll see that the intercept term might reflect an overall positive bias that the participant may have, which may be because they're a very nice person and they don't want to call anyone negative, or they are, otherwise think that that's what the experimenter wants, and so on. But it hasn't got to do with their underlying values. Okay, and what we find now, to my slight distress, at least to start with, is that this rather simple value partitioned reinforcement learning model does just as well as the classify refine model to explain the data. So the dots here are equally distributed on the two sides of the line with respect to which is the model fits. Okay, so this was the first study that we did with this. This is the first analysis with this particular study, but actually we wanted to apply this task and the modeling to adolescents, and we were interested to see what happens if they are low in mood. So we have this replication and extension study of the same. On 122 young people between the ages of 12 and I think it's 15 by Christina Carlis's team. And first of all, here we replicate rather nicely that the classify refine model outperforms the fine-grained beta belief model. So you can see that the dots here are all pretty much all on the side of the, well, not all, but the majority of the dots are clearly on the side of the lower BIC for the classify refine model. So that's good. But again, the simple value partitioned reinforcement learning model does just as well as the classify refine model overall. And the black line here is a simple linear regression line. And I have plotted to show that maybe we can get a sense that as the fit gets better, as we describe more accurately certain participants' behavior rather than others, the classify refine model itself does a bit better, and vice versa. If we are above the mean of the BIC for classify refine, that's to say the people that are not fitted quite as well by either model. So that's puzzling. Okay, these kinds of models are both value partitioned or valence partitioned, but they are different. So I am interested whether there is a deeper reason why the one approximates the other as well as it does. And I wonder if we could conjecture that the associative learning model constitutes an approximation of the effects of uncertainty in the Bayesian model that are inherent in both the beliefs about which state is there, but also about how positive the outcomes from each state. So both from the, I wonder if the associative model offers us a sort of an approximation of the combined effect of the two. Okay, and maybe it actually reflects the accumulation of evidence into each of the model, into each of the channels. So maybe there's a correspondence between the positive channel in the one model and the positive channel in the other model, and similarly for the negative one, or maybe not. Maybe it's just the difference that corresponds. So finally, I come to the temporal difference story. And I am wondering whether what I'm going to say now is about people learning or inferring more accurately about the actively attended state that they're in. And they actually have to make effort, cognitively at least, to propagate this knowledge, to trace its consequences for other states, particularly states leading up to where they are now. So just to remind people who may not be so familiar, in temporal difference learning, we represent time as a series of fairly fine-grained time steps. So unlike what we've talked about so far, we're not talking about what people learn or infer over the whole trial. We don't do Rescola-Wagner or the sort of the beta belief model that I've described. We are chopping up the trial into time slices, and we see how learning propagates over those time slices. And this is the famous Bellman equation rewritten, that when we have arrived at a situation where we have learned as much as possible about what's happening under a particular policy, pi, that we are following, then the value that we attach to a particular state at time t, which is on the left-hand side of this equation, equals the expectation of the return from that state plus the discounted value of the next state that we're going to get to if we apply this policy pi. And gamma here is a temporal discounting rate. And upon taking a time step, therefore we experience a prediction error. But this prediction error is a little bit more complex than the reinforcement learning standard one, which is just return minus expectation. But here it is a return plus the discounted value of the next state, that's the first and the last term on the right-hand side, minus the value that we held for the state that we came from. And this, applying this, allows us to update this value of the state that we came from. And for some reason, the graphics failed here. But this should say basically that V is equal to a learning rate times the delta. So it's meant to be a very, very simple equation. And interestingly, there is some neurobiological evidence for that. So Paul Sands and his co-workers measured dopamine release using intracranial electrodes in people, and they found that they got a clearer correlation between the electrochemical signal and the computed reward prediction errors in their associative model if they calculated the reward prediction errors at each of several steps within a trial, each trial that they considered. They didn't consider the trial as a whole, they considered these sort of finer states within the trial. So here's a task that we are doing at the moment, which also has naturally has several states per trial. So this is again a social task, and we have blocks where in each block there's an advisor. And the advisor is the person whose picture you see on the screen. And the participant is asked, first of all, of their expectation of how good the outcome of the advice is going to be. And that's the first slide rule there, which is marked as S2, state 2. So what is their expectation of the outcome of the advice? And then they observe whether the outcome was great, or it was so-so, or it was negative. And then, having they see that within the same trial, they're asked about the probability that the underlying person, the underlying computer partner, is good or bad, is caring or uncaring. And then there is the next trial, for 12 trials, and then the next rater, and so on. But as we had the results that I showed you about the active inference, first of all, model, here we explicitly taught participants what the likelihood map was. Okay, so they did not have to gradually learn that over trials. We serve it to them. We tell them there's a positive, a caring person or an uncaring person. You have to find out who it is. And this is the likelihood map. And as you can see, the likelihood map is a little bit subtle. It's not hugely easy to tell between the two raters, except when there is the very negative outcomes. And the very negative outcomes are much more characteristic of the uncaring advisor. And now we again compare models, but now we compare a temporal difference based Bayesian model, which I'm going to tell you about the formulation in a minute, to the standard trial-wise model. So the trial-wise model says that the participant infers on when they see the outcome, they make an inference about the rater, and that is their belief about the rater until the next update. Okay, they don't have to propagate this belief in any form among different states that they may find themselves in. Okay, why should they? Whereas the temporal difference formulation says, no, they have to actually work, and they have to remind themselves in some way, they have to learn in some way again what the underlying causes of the world is in different states. And strange as though this may seem, a model that has got this temporal difference component here does much, much better than the whole trial model. And this is how I sort of trying to translate the temporal difference associative modeling to a Bayesian formulation. So first of all, I am writing down here Bayes' rule for the update of the belief that the underlying person, the underlying cause is caring. So is the advisor caring given an observation? So We write down Bayes' rule as we all know and love it. And now I'm going to divide throughout by the numerator. Okay, so one of the terms in the denominator is going to be 1 because it's the same, and the other one is going to be the ratio of the two. And now this ratio of the two, of the essentially about the joint of the observation and the cause, we can express as the exponentiation of the respective log. Okay, now this is a roundabout way of doing it. Why should I take the log and then exponentiate? I would get back the same thing. But when we show it like this, we see the relation that this now has to the standard basic softmax that we use, or otherwise sort of the Gibbs function that we use so often in neurobiology. And we see that this log probability naturally scales as value. So once we have observed that, I can take this and this value, which is the log of the joint, or in other words, the unnormalized posterior, and use it as the thing which TD is going to propagate. So here again, I'm sorry about my graphics have got a bit distorted for some reason. When I update my belief about the underlying cause, I do that in terms of a log expectation, an unnormalized log expectation, which I'm going to call R plus. And at the same time, I do the same for the R minus. Okay, so that is different than the associative learning thing, which only in the value partitioned scheme, they only updated one but not the other of the channels, depending on the receptive field within which the observation landed. And now I can use this value-like or return expectation of return-like quantity in the standard temporal difference updating scheme to form, first of all, a prediction error for the positive channel, which I have denoted here as delta plus. And to here, and to multiply this with a flat learning rate to update my values for the states leading up to the state where I made the inference. Okay, so here, for example, if I received the outcome, I made the observation by going from state 2 to state 3, I am going to update state 2 by this based on this prediction error. And as said, this works, and it doesn't work, however, again, any better than the standard reinforcement learning, or rather not the standard reinforcement, the temporal difference reinforcement learning model. So here in black was the same comparison as I showed you before, showing the superiority of the TD-Bayes. But now in red, I am plotting the TD-Bayes against the value partitioned reinforcement learning, and I find that they do just as good a job in terms of model fit in this simple model of simple measure of model fit as each other. Okay, And how good is the actual description of the data? So in an experiment that we are now doing for EEG actually purposes, we've collected some data, and this is an example of it. So on the left, you see the course of the participants' answers discretized in these red circles, dark red circles. In pink is the prediction of the Bayesian model, which isn't discretized. And in yellow is the associative, or gold is the associative TD. And you can see that they both do a pretty good job at describing the data. And furthermore, the predictions of the two are highly, highly correlated with each other. But if I then go and look under the hood on the right-hand side, you will see that the positive, the positive, the values of the positive channel that underlies these decisions, or sorry, the negative channel. Sorry, start again. The values of the negative channel in this example are not correlated between the two models. Sometimes we can see a positive correlation, sometimes a negative one, but on the whole, we just don't see anything like this tight correlation that you see on the left with respect to the actual outcomes or decisions. So my question here is whether we should take this seriously and use neural measurements and try to measure the neural activity in the positive and negative channels to tell over and above the behavioral manifestation whether people do a temporal difference Bayesian update in this interpersonal domain. And that's it. That's my questions and my presentation. And thank you all for your time. And special thanks to all these people that have helped with this work.
Thank you so much, Michael, for the presentation. Super interesting. So we're gonna move now to the questions, discussion. So if there are any questions in the chat, like feel free to raise your hand. So I just have like just about the very last thing you said. I'm just curious. So you're saying that you have these two models that both seem to be fitting the data like equally well?
Approximately equally well.
Approximately, yeah. But then once you look at the predictions at each of these, like the negative and positive, then they seem to not be doing so the mechanism to get to that same solution seem to be different. Is that the kind of thing?
Yes.
So then the neural data would be to say, okay, I'm gonna add this extra like data that I have and see which of these models can predict that more accurately. So then I have like another measurement to say, okay, this model like Bayesian, for instance, seems to like match exactly what the actual brain is doing, right? Something.
Yes.
Is that the okay?
Exactly.
And are there like any like intuitions or expectations about what would you expect in that, like if you run that experiment? Do you have any expectations?
Well, my hope and my expectation eventually might be that if we look at these intracranial electrodes that appear to measure neural activity which is associated with prediction errors, then the Bayesian model will do a better job at corresponding to weighed prediction errors that these updates might so basically we're going to see something which is more like belief updates that are proportional to prediction error times a weight, which is what you would expect from a Bayesian perspective.
Okay, okay. So, yeah, so you're expecting that kind of belief update kind of sort of computations happening there. Right?
Hopefully, yeah, that's the
Yeah,
hope.
yeah.
Yeah.
Yeah. Okay, nice. Yeah. Interesting. Looking forward to see what you get from that. That seems quite interesting.
Thank you.
Yeah, let's see. Are there any questions in the chat, in the audience? Oh, Andrews, see you have the camera on. I don't know if you want to ask anything.
Yeah, well, I thank you for the talk, and this is new to me, but this may relate to a theory I'm working on about three minds. So this is like a metaphysical approach, but it would say that for human experience, we need a mind that has answers, a mind that asks questions, and a mind that relates them to investigating. Or another way to think about that, a mind that unconsciously knows the answers, a mind that doesn't know anything, so it's consciously asking, and a third mind that decides which mind is more appropriate at either time. So this would suggest that in the case of you're saying with these two channels, the mind that knows is the lucky mind. And so if everything's going lucky, you want to go intuitively. And if you feel, let's say, if maybe for a person like me, positive evaluation would be the lucky mind. But the mind that does not know is creating these artificial tensions, saying, look, you have to be careful. Things could be unlucky. And so it strain this lucky mind and to look problematically. So that for me would be maybe a negative mind. Now, for a particular person, it could be the opposite, depending on how much they've been abused. But then there's a third mind that integrates those two. It decides, well, is this my lucky day or is this my unlucky day, or moment by moment? And I think I also notice, so I think that would, is it the TD-Bayes model that's the double channel model?
Both the associative and the Bayesian models that perform well have got separate positive and negative channels.
Oh, okay. Okay, so then I don't know how to think about that in those terms. But I wonder, I'm curious if you think of this may be a naive theory, but I'm curious if it relates to what you're doing.
Well, I'm particularly curious about the integration that you've put forward, in the sense that there are these sort of component there are these component assessments that take place that you may not be fully aware of, and that there is some kind of mechanism that you put them together. Now, in what I did here, I said that essentially this is where Bayes' rule comes in, so that when you perform the computation to get a Bayesian update, you have to get these components and put them together. So here is the one component, and here is the other component, and here's Bayes' rule. So presumably you may be able to do this well or not so well to integrate those those more latent assessments.
So the way I think of Bayes or etc. like with this, I think of in terms of active inference, I think of like the answering mind as basically the environment. The unconscious mind is kind of like meshed with the world. And I think of this chasm, and what we call the organism, let's say, is the conscious mind. It's divorced from the world. So the generative model is the approach of the conscious mind, whereas the unconscious mind, I kind of think of it as just like a weighted average neural network doing, spitting out whatever. It's like it's representing 100 billion neurons, whereas the other one's representing 100,000 concepts, let's say. And then neurologically, I would think that we have two brain hemispheres, and in terms of implementation, it's not clear why. But in terms of user requirements, it would be clear why. Like you need to put the same information in two different forms, what you know, what you don't know. But the right and left hemispheres are just projections. That's not where the consciousness is taking place. I think the consciousness is taking place, the integration is taking place like in the basal ganglia, for example. So humans have this wonderful simulation that we live in. It's just profoundly vivid simulation. But consciousness-wise, we're just the same as any other creature who's got a basal ganglia or something like that. So I think the TD-Bayes model, I think it's looking at it from the generative model point of view, from the consciousness point of view, and there could be another side that's looking from the other side's point of view, and then they basically should be in sync. So that's my babbling.
Thank you.
Thank you. Ian, you have your...
Yeah, I just wanted to say that your presentation was really excellent. It was very interesting and it stirred a lot of thinking. And I was thinking whether if your valence-partitioned associated models, those associative models, whether if would you think of it as an extension of or much more preferable than just a typical Rescorla-Wagner model that has been implemented since 1972 when it comes to understanding those predictive learning behaviors? Do you think of it as something that is much more efficient than those traditional models?
Well, I mean that's more of a historical question for the reinforcement learning community. I'm not quite sure how what the history went. As far as I know, the original Rescorla-Wagner formulation, if I can actually bring it somewhere, was before these sort of issues of mathematical consistency, were thought about. So no, I don't think that anyone actually thought, does this make mathematical sense? The temporal-difference formulation is more rigorous in that it takes into account the time dimension quite explicitly, but also that the learning rule is essentially a consequence of it aims towards achieving this consistency of the Bellman equation. It's a sort of a way of satisfying the Bellman equation by doing rather than by thinking, by actually visiting those states and learning from experience. But that's why it's not efficient in terms of it normally takes...
Of addressing the question that you're trying to, in terms of addressing the research question that you and your team are trying to answer, the Rescorla-Wagner model might not be as sufficient as the temporal-difference model and the valence-partitioning associative models. Is that correct? Would it be fine if implementing these types of models, not only in analyzing human behavior, but also analyzing behavior between humans and large language models or artificial agents? Would that type of reasoning be perhaps very interesting, since this is a very trendy thing today, and the question about ethical decision-making or decision-making in general when it comes to artificial systems is often in question? And would you consider these models as a quantitatively robust way of addressing these types of interactions and behaviors between humans and computers or artificial agents or agentic AI?
I'm not a deep learning person, and the sort of the joke is intended here. But but to the extent that I can actually um, comment on this, I think it's actually the values that the objective function which is most important, rather than whether we implement it so as far as the sort of whether the interaction between a human being and AI is to the greater good. I think it's the objective function that the AI is trying to implement, that's most
Okay.
important. In fact, I think there was a presentation about that a little while ago in this forum.
Very interesting. And overall, I thought your presentation to be very interesting and very thought provoking, but not provocative. It stimulated a lot of thought. But just one final question. Would you think when it comes to implementing these models, do you think it would be possible to implement these models through Python code from scratch and work on
Yeah,
these models? Okay.
yeah. I mean,
And create simulations and all of that type of stuff.
totally, yeah,
Okay, perfect.
yeah.
Well, that will be an interesting summer project for me. So,
Yeah, I mean, my code is in a mixture of R and MATLAB, and some of it uses the off-the-shelf active inference, and some is so it's not all sort of nicely laid out. But if you want me to give you some of this code, it's perfectly readable, and yeah.
well, thank you very much for your comments and answers. Yeah.
Cool. Thank you for your question. Let's see. Does anyone else? And if there are no more questions, then I guess we can pass it on to you, Carl.
Could I just make a quick comment? I'm familiar with Norman Anderson's information integration theory, and I'm wondering if the speaker is, and I think that the same data could be maybe just interpreted to see if it works. Because there's a fascinating theory in that he would show like when does the mind use averaging or addition or multiplying in maybe 100 different cases, with his graduate students. And you get the sense that when people say, they rank 7 out of 10 something, that there's actually a number in their mind, that they're accessing something that's deep in their mind. And so a typical example would be like if you give someone a gift of a diamond ring, let's say it's 10 out of 10. If you give them a pair of socks, it's 2 out of 10. But he would say, well, what if you give them both? And then it turns out people average, the diamond ring with the strange things like that. But that the number seems to be in the mind, and very much like in your research. I'm curious if you're familiar with that.
No. So that, yeah, it's an interesting idea, and it's an interesting idea with respect to the fact that in the task that I described last, we actually teach people the likelihood, and we kind of expect them to make predictions on the basis of that. And maybe they don't. Maybe they integrate the observations that they see along a much more idiosyncratic framework, a little bit like you described. Although the fact that these models, in some cases do as well as this, suggests that they're not that off.
But I think that what he would find or something with that is that it's very interesting that you made those proposals to the people. And I think what he'd find is like, that's sitting in their brain, and then the other things are coming in their brain, and they're like averaging from both or something like that. And then you can be very refined in terms of like what's to figure out like how are they averaging that and what's happening, and or is it averaging or is it multiplying or is it additioning? very sophisticated. I put a link in the chat, and
Thank you.
Just one final question surrounding this study. Have you considered the occasion of trying to implement this type of experimental design in task-dependent neuroimaging fMRI analyses to identify which brain regions are in fact activated when it comes to these underlying behaviors? And have you also considered implementing other neuroimaging-based tools such as EEG or MEG? It would be very interesting to further test these quantitative models in addition to the behavior-dependent models that come from these underlying analyses. Does that make sense? Or
Yeah. So we are. I mean, the thing on the screen is from an EEG study, which we haven't actually analyzed the neural side yet, and this is with Adrian, who's in the audience at the moment. I said there's a collaboration with Paul Sands to give this task to people that have deep brain electrodes where they can do electrochemistry and see how 3 different monoamine neuromodulators correlate with the prediction errors or the weight prediction errors that I described.
Okay.
But no plan for fMRI as yet.
Okay. I see that one of your collaborators is Dr. P. Reed Montague at Virginia Tech. I'm very familiar, and I sincerely appreciate his work as he collaborated with one of my mentors at the University of Virginia, whose name is Dr. John Van Horn.
Okay.
But this is very interesting and stellar work. And with that said, I have to leave now. I hope you have a wonderful rest of the day.
Thank you.
Thank you for that. Yeah, I guess now we can move to you, Carl.
Thank you. It's my turn now, is it?
Yep.
So I think Michael had he's brought some questions to the table. And there seem to be sort of 3 levels that we could discuss in terms of the questions that could be addressed in terms of the three sort of models and bodies of work. Michael, would it be all right if we went back to the sort of the denouement of each of the 3 sections and sort of just revisit the key questions that you'd value discussing?
Okay.
Yeah.
If I manage to make this work. Okay, so the first question was this is this sort of essentially categorical structure inherent to the social brain, more or less?
Yeah, and that I think that sort of fundamental question seems to be a cross-cutting theme throughout the 3 bits of or the 3 perspectives. This notion of what is the structure or the implicit structure of the generative models that best explains the responses or inferences or choice behavior of the subjects, and then the other sort of common well, perhaps emergent theme towards the end is how could one look at neuronal, electrophysiological, or neurochemical responses to disambiguate between the different structures that that emerge. This particular, the first question then. So if I understand it correctly, what you're asking is is the structure of the generative models that we bring to the table in order to classify things, in this particular instance, classify people in terms of their tendency to rate other people positively or negatively. Is this structure best thought of in terms of some fine-grained continuous classification, or some coarse bipartition, or, as you seem to be intimating, a composition of both, in the sense that within a coarse-grained categorical, you can now have some more fine-grained continuous representation. So would that be a summary of your conclusions, that when you put models to these data, those that have both a categorical aspect and a continuous fine-grained aspect seem to explain the data better?
So that was my intuition. My intuition was that this distinction between inference and learning, and in learning being a slow inference over a sort of a different time scale, that would be that would be necessary, and that actually worked to a large extent. But I was surprised at how well this kind of associative approximation, which hardly has I mean, you can say that it may have some sort of vestiges of a generative model, but it's not really explicit. I was surprised that it did as well as it did.
Right. I have to confess, it didn't surprise me. And if I mean, perhaps if I explain why it didn't surprise me, that would give you some something to write about, or something to discuss as a viewpoint, or indeed point a direction forward in terms of empirically taking this forward. And so I'll explain why it didn't surprise me. First of all, you are focusing on learning, not inference, but you're doing it in a way where basically the subjects are obliged to learn to infer, in the sense that they are making decisions on a case-by-case or trial-by-trial basis. But the key belief updating is not the inference process, it is the accumulation over multiple trials. So that license is now the application of things like the Bellman optimality principle and Rescorla-Wagner and sort of reinforcement learning approaches, which coincide with a more generic active inference and learning approach. So it is straightforward to show that in the limit of an absence of ambiguity or uncertainty, the Bayes optimal learning in the context of active inference and learning, if we subsume learning in that, just is the updates that you'll get from the Bellman optimality principle. And under simplifying assumptions, that just is Rescorla-Wagner and the like. So it doesn't surprise me that you can fit the learning you can fit the data with a conventional learning model that's focused on learning to make a decision. The other reason I'm not surprised is that it's not just any old learning model. It's this sort of two-channel positive and negative categorical learning model. So you're bringing to the table now a learning model that has exactly this mixture of categorical coarse-grained classification and continuous fine-grained classification, simply because reinforcement learning models and all the sort of effectively the trace representations, things like Q learning and Q learning and Rescorla-Wagner and the like, they all deal with continuous variables. But as soon as you have a distinction between Q superscript plus and Q superscript minus, so as soon as you introduce a parity for a categorical distinction between up and down, plus or minus, negative or positive, you've actually now got two continuous learning schemes. But now, by definition, you've now got a hybrid scheme with both categorical and continuous bits to it. So I am not surprised that you were able to fit the learning data with that kind of finessed classical reinforcement learning model, in as well as you would with the explicit active inference model with the right kind of generative model. And what is the right kind of generative model? It is simply that which has a coarse-grained bipartition, and then nested within it finer grains, and you can imagine unpacking that down hierarchically to even finer grains should you want to. So that didn't surprise me. So for me, the interesting question is the structure, the implicit structure of the implicit generative model, and that is being disclosed by the way in which people learn. And that's very much how you started, by noting this knee and this sort of this kind of learning that could not be explained under a vanilla continuous state space value learning model. There was something more structured going on, and the structure you've alighted upon is this compositional kind of generative model. So you could represent this in many ways. My mind goes immediately to sort of a hierarchical generative model with good and bad, and then within good and bad there's shades of grey. But the hierarchical inference, the good versus the bad, is a very fast inference, and that contextualizes your subsequent more fine-grained classification as more evidence comes in. So by introducing this sort of depth to the generative model, you're rendering it effectively semi-Markovian, and therefore you can now reproduce or fit this sort of biphasic kind of, as you put it, you can fit the knee, and that to me I think was a compelling observation, and it then begs the question, is a particular sort of bipartition with some fine-grained stuff underneath, is that the final solution? Or could you now explore other kinds of sort of compositional models that have a nesting attribute, and use the data to explore a space of models that had different kinds of structure? So that what I'm asking you is, do you need to worry about is there any real difference between the parity or the two-channel reinforcement learning and the Bayes, I can't remember how you described it now, but the sort of the Bayesian inversion under a course, under a fine-grained generative model?
So is there a difference? I mean, there are similarities between these models. Like, of course, they have these categories that accumulate things, but they have differences that I thought might make a difference. So, for example, the key one is that the active inference model doesn't have observations that it says I'm going to ignore this observation. That this observation is actually not going to update a part of my small a map.
Oh, I see. Yeah, but could you not? But that's your interpretation of the two-channel reinforcement learning, isn't it? When you say the ignore, you're referring to the how you've implemented that sort of was it Valence-partitioned scheme?
Yeah. I took that from Paul Sands and Reed, Montague, and co.
Yeah, I mean, I think this sort of, separately updating two channels is just the same as sort of having a categorical distinction, and then with it having made a categorical distinction, then within that particular categorical distinction, then doing your fine-grained learning.
Yes, that's what happens in the active inference one. But it seems that the reinforcement learning one is a bit more coarse, that it's, it only updates within those receptive fields.
Right. Well, yes. So the receptive fields you can think of as the coarse partition. So you commit to one or the other.
Yeah.
And then you just do your continuous fine-grained learning within the one or the other. So you're conditioning. So you can look at this as deploying a Rescorla-Wagner model conditioned upon it being in this course category or that course category. And then you put them back together when you do your, I can't remember, it was a softmax operator on some weighted Q plus and Q minus.
Yeah.
But mathematically, that's just the same as sort of, well, it's not just the same, but it is an approximation to, first of all, making an inference whether it's positive or negative, then conditioned upon that inference, then making a finer grained inference, given that it is positive, whereabouts in a more fine grained sort of quantitative scale, would I put this?
Yeah, that's right. Again, the other caveat is that the reinforcement learning model doesn't know about the distinction between a cause or a state that is more positive and just a bunch of outcomes. So that it doesn't have that that layer of what is the cause of observations, which I thought would maybe a different task would bring it out.
Right. So when you say bring it out, are you implying that there's something fundamentally different about the reinforcement learning scheme in terms of the way it describes or behaves the learning relative to an appropriately configured Bayesian learning scheme or active inference scheme?
Yeah.
Is there something you've learned? Is there a hypothesis generated by the fact you can explain the data using this valenced reinforcement learning scheme that you can now test by looking at the implicit generative model and comparing it against another generative model? I guess what I'm saying is here, these reinforcement learning schemes just describe the data. They don't give you any mechanistic insight, and they're unexplainable in the same sense that a large language model is unexplainable. They're just descriptions. Whereas if you commit to a generative modeling approach, you now have an explainable teleologically in terms of belief updating, in terms of disambiguating between inference and learning and the like, and crucially, the ability to find the best generative model that explains the behavior. So that's why I'm asking, what can you frame? Is there anything interesting in the reinforcement learning fitting of the data that would speak to a space of generative models that you can now test using active inference? That's where I'm driving. So if you could, in the spirit of computational phenotyping, fit the learning data under two models using the same Bayesian scheme, where one model, for example, had no coarse-grained partition, but had lots of fine-grained partitions, and then the other model had this coarse-grained partition, and you conditioned your fine-grained representation on the coarse-grained, so that then you could do a model comparison when you optimize the models to explain the choice behavior. And you will hopefully get better fits of the learning curves with the model that has this categorical or hierarchical or compositional structure relative to one that's not got. And then you could say, you know, using Bayesian model comparison, I now have evidence that these subjects are using this kind of generative model that has this separation of scales in play, or this compositionality, this sort of coarse and fine-grained representation of the space, in this instance, of valence responses or judgments of the raters. That would be, you know, that would be one application that would address an interesting question from the point of view of the structure of the generative model. However, it's not terribly interested in the fact that the reinforcement learning fits the data as well as a Bayesian model. So I'm just trying to get a sense of what is the interesting question from your point of view.
Oh, my interesting questions, apart from what is on the screen, is first of all, can we go to the neural level to disambiguate? So that's actually a very important question. And a curiosity, which isn't as important a question, but it's a curiosity, is to understand a little bit better the mathematical approximation. So if it's an approximation too, then, you know, how does this approximation work? But that's more of a curiosity. So, for example, I know that there are particular conditions of volatility, for example, that where a constant learning rate is optimal. So a model with is very simple and it's got a constant learning rate does as well as any other. But here I don't have that kind of intuition. But my main thing, unfortunately, I have to say that I have to, much as I absolutely love the discussion, I need to go at 4 o'clock. So I suppose my key question is whether it's possible to use the neural data to tell. So should I believe the innards of these models? Should I believe that these sort of the values that these models use to make their predictions are different, and look for those underlying values in the brain in terms of neural activity?
Given we've got 8 minutes, yeah, absolutely. However, I wouldn't use. I'd put aside your curiosity about Mascora-Wagner and all those lovely variants. That's not going to get you where you want to be, because they don't have associated process theories. So one gross error that people have made is associating dopamine with prediction error. It's not. Dopamine is the precision. It's the learning rate. So you now have to look at the underlying maths from a completely different perspective, which of course is a generative modeling perspective. And once you've got the right generative model that has now been optimized in response in relation to behavioral or choice responses, then you've got now, if you've fitted your generative model scheme, your Bayesian scheme, in a way that you've now reproduced the subject's behavior, you can then just now look for the correlations between the neuronal responses and the simulated belief updating. So I said before that, you know, reinforcement learning models are not process theories. The advantage of the active inference models is they're well-defined process theories. They can simulate LFVs, they can simulate phasic discharges, they can simulate synaptic efficacy, they can simulate learning very, very explicitly, provided you can actually simulate the trials and the paradigm, which I imagine in this instance you can. And then all you do is you're just looking for correlations between the neuronal responses and the distributed patterns, say, of neural activity, or on a longer time scale, the correlations between your measures of effective connectivity, say using DCM, and the increases in the connection strengths implicit in the accumulation of Dirichlet counts. So you could certainly do that in a really informed way, and you don't need to throw away the behavioral data, because I think you'd be using the behavioral data to optimize the parameters of your generative model to get the priors right using the computational phenotyping before you then took a canonical example from what the subjects actually experienced, and then you just look for correlations in the usual way. I mean, this is going back to the inception of computational fMRI, but you're not using now Riscola-Wagner models because there's no process theory. You're now using active inference in order to generate explanatory variables for the electrophysiological or the fMRI or or other features based upon, say, for example, effective connectivity or changes in effective connectivity. I think yes, absolutely. But notice you're not sort of a priori saying, I'm testing the hypothesis about this and that. You're just letting the data tell you. You just find out where in the brain has this particular time-dependent pattern of, say, event responses emerged. So you've got a synthetic brain that's actually doing what has to be done, that's now been optimized or personalized for this particular person, given this particular paradigm. A very large multivariate characterization of the belief updating that has to be there somewhere. And then you've got your multivariate electrophysiological or fMRI data, and then all you need to do is to pair them up. And in so doing, you now be able to have something that is explainable in terms of the subjective belief updating, subpersonally usually, and learning, because you've actually got an explainable generative model explaining the choice behavior that you can now map onto the anatomy of your neuroimaging, the neuroimaging data. So you now got a true structure function mapping where the function can now be articulated in terms of Bayes optimal decision making and learning.
Yeah, makes sense. Yeah, makes sense.
It would require you, though, to do your computational phenotyping. So fitting the choice behavior to the Bayesian models by adjusting the priors. And coming back to what I thought was an intriguing point, part of those priors is the very structure of the model itself, having this divide or the separation into sort of coarse-grained and fine-grained, where the coarse-grained is contextualized in the fine-grained. That's quite a sophisticated structure, and you need to establish the evidence for this, but also explore it. I've seen similar things in terms of characterizing unit responses and electrophysiological responses to visually evoked responses, and looking for evidence of sort of carving the receptive field up into quanta. And sometimes I remember, it was Samuel Dawes' friends, I can't remember who it was, but there was a really interesting little literature suggesting that the brain actually does quantize stuff. It does carve nature at its joints into chunks, and that many receptive field responses can be better explained by a chunky carving up as opposed to a continuous one. And then the question is, how fine-grained, how many chunks? And that, to my mind, if we'd had time, what was going to press you on is, did you explore different Bayesian models with, say, just good and bad, or good, bad, and intermediate? And then with good, bad, and intermediate, or just good and bad, did you have, a bipartition, or did you have 3 chunks to that, or was it continuous? Was it effectively 8 chunks? Because all of these speak to different kinds of structure and different kinds of resolution, and all could be very plausible models of the way that we carve, in this instance, the social nature of judgment at its joints. And of course, we don't know what the most parsimonious, minimally complex generative structure of the generative model will be. I mean, you've got some good clues here, but it'd be really nice to chase that down just by using Bayesian model comparison to actually try and fit the data with a little family of models that had this compositional deep structure, but just say, is it just good and bad, or is there we've heard from Andreas, in terms of the three brain, in a trivial interpretation of that, you could have committed positive, committed left, and not committed ignorant. So all of these are, I think, exciting opportunities for you now to sort of just pursue this sort of notion that our generative models in this particular space have much more structure than people previously anticipated, and then provide the evidence for that. And that's just with the first one, so we haven't got to your second two experiments yet. You'll have to come back.
Oh, I'd love to. I'm sorry I have to rush, but I would love to. Is there a specific focus that you would like me to? Well, I could easily update people on how the experiment went and what the model comparison is like. I think that would be a...
Yes.
Yes.
Yeah. Well, we haven't really discussed the temporal difference aspect, and that would be, I think, something that we should discuss as well. But yes, perhaps it'd be wonderful to have you come back. Word of advice: perhaps it's slightly less material to chew through next time, and then we can sort of feel that one part of this has been brought to closure. That would be wonderful.
Okay, thanks very much. Sorry about that. I didn't realize. I thought you actually made a fairly short presentation by my...
Well, it was short, but it's still a lot of material.
Okay. Thank you so much for today. I'm sorry I have to go for now. Is that okay?
Well, yeah, thank you so much, Michael. See you next time then. Thank you, Carl. Thank you, everyone.
Thank you very much.